So now let's look at the structure of the model. In order to do that, let's do let's see model summary. Okay. Then actually we need this one, model summary. So yes, sequential model, and then yeah, parameter, number of parameters. So we have a lot of parameters to estimate. So already model is very complicated, maybe too complicated. Let's add some dropouts. So here, model add drop out. Okay, drop out of 25%. So it randomly selects 25% of nodes to avoid overfitting. Okay. And then let's add this one over here, and then let's add dropout over here. Okay. And then let's run the program very quick. Good. And let's see the model. Okay, good. So we drop the parameters. That's fine. And then next, we have to see the result. So I wanna compare in-sample result and out-sample result when we run. Okay, the number of running is epoch. So as epoch changes, we wanna see how the learning performance changes. So first, we have in sample y and out of sample y. Okay, in sample y and out sample y. So this is y we predict in the in sample. So model predict. So with training set. And then this is now predict model as test set. X test, we didn't use this data for training. So it is like out of sample test. Now we can define errors, in sample errors and out of sample error, in sample, and then out sample errors. And then this is the, of course, difference between the predicted y, right? And then predicted y and then observed y. So y training set, y in sample, so train minus in sample y. Wait, I have to check the y. Let me check the shape. It's 900. So let me see whether it is correctly determined. Yeah, it is not. So it is 901. So I need the entire row and then first column. Okay, now it is fine. And then out of sample, out sample, in sample, out sample error. And then is test set. And then out sample. Okay. And then yeah, out sample y. I can see I can compare the performance. And then mean squared error is basically squared of the errors. So mean squared error of in sample is basically average of error in sample square. Mean squared error. And then similarly, I can check out sample. So here out, and then average out of sample out, and then we can check we can see the result. So let's say print, and then MSC in sample equal MSC in sample, and then MSC out sample, basically test set, MSC at training set equal MSC at out sample. Interestingly, we have, well, interesting. So yeah, actually MSC is smaller at test set. So the deep learning model performs even better at out of sample. Well, that can happen because we have a small sample size, I guess, small sample size. And then, well, we didn't, maybe learning is incomplete, maybe. Or maybe pure luck. That can happen. And then let me visualize the result. Let's visualize. So let me check the name of the, keys, history, and then keys. Okay. Yeah, so I need a rows and validation rows. Okay. And then let me the code for graphic. Well, let's import the usual visualization tool, matplot library. So import matplotlib library as plt as usual. And then to make it pretty, import cbone. Okay, import cbone. And then plt style use cbone. And then about rows function, rows is is the history, and then rows. Okay, and then let me see the rows. Okay, so plt plot rows, and then plt show. So the rows looks like this. So yes, that's good. As the increase epoch, yeah, we have smaller rows. So the machine is clearly learning. This is not bad. And then next we can compare this one with validation loss. So let me copy. Basically, it is the loss in the training, right? It's a training loss. And then we have validation loss. Validation loss. Okay. And then epoch. Epoch is epochs. Epochs range. Range of the training loss. Training loss. Right. I should do length. Length of the training loss. Okay, that's fine. Okay. And then because I want to start it from 1 and then plus 1. Okay, so that is start from 1. And then let me show the graph. So PLT figure. It is not necessary, but let me show it. And then first, let me show the let me see the training loss plot. And the first one, x-axis is epochs. And the y-axis is training loss. Training loss. And then shape of the graph is blue. And the label, let's put label. Label is training loss. Okay, good. Training loss. Well, that's exactly the same one. Okay. What if I put O over here? Yes, let me try this one. And then next, validation loss. And then let's say red. First training loss, so now validation loss. Okay, like this. So validation loss also decreases. Let me this is better. Let me see. Yeah. It doesn't make much difference. Okay. And then here, let's put title. Title. Title is, of course, training and validation losses. Training versus validation losses. So we have title. And we need a name for x-axis and y-axis. PLT x label. X label is of course epochs. And PLT Y label is of course loss. And then I want to still legend. Right, train loss, validation loss. Right, and this looks fine. And then Actually, I wanted to see the statistics. So let me see the statistics. So print out sample errors, and then print the name was error is this one, error out sample, right? Error out sample. Print. Now I want to see the statistics. So error out sample and describe it. So out sample error count 100 and mean standard deviation minimum median is this one. The slight overpricing. And then print in sample errors in sample and describe it. And then I have a 900 and then mean is this one and median is this one, right? And then yes, standard deviation. Okay, I can see the statistics. Okay, it is useful to track the errors. Finally, let's the distribution of errors, right? Histogram. Okay, let's generate histogram. Okay, we have statistics over here, so I can see we can see the distribution, but visualizing the distribution is always helpful, right? So PLT histogram, PLT histogram, and then of course first out of sample, error out sample, and let's take a look at it. Looks like this one. Okay, color is okay. Let me make it clear. Pretty one, color sky blue. Yes, sky blue. Okay, and then bin auto. It doesn't matter. Bin auto is actually bins. It should S. Okay, that's fine. Array. And then PLT histogram, and then in sample errors, and then auto sky blue, and then instead we say well, yes, and then this one looks like this one, and the first one, okay, PLT show, and then next one, I want to see both of them. PLT show, okay, looks fine. So errors, first one is in sample, out of sample errors. Let's do in sample errors. So, well, if our learning is perfect, it should be around the 0, and in sample is around the 0. Of course, there are some big errors. So definitely we need more training and more data in this case. Yeah, let me add the title. So it is a test set. Yeah. Error, pricing error distribute histogram at distribution. Okay, distribution at test set. It is the test set, and then this is the training set. And then let's run it. And then, yeah, rightly. And then everything looks fine. So, of course, I want everything around this one. In order to do that, what we can do is, of course, well, here, maybe we can make more complicated. Actually, I can delete dropouts. Let's try this one. And then if we run the program, if we run all, let me see whether we have slightly better result. Okay. So, well, not much different. Definitely it is better in an in sample, but out sample, I'm not sure. Out sample, I'm not sure. In sample, because we have more parameters, it's better, but out sample, yeah, we cannot sure. So let me put it. Okay, so I think we need more data, and then we have to calibrate model better to make it better fit, but I think it is enough for today's class.